Today's lesson is the first part of a two-part series focusing on oxidation and reduction reactions, also known as redox. In part one, we are going to focus on understanding what these terms mean and also understanding the components of a redox reaction. Let's take a look at our learning targets. After today's lesson, you will be able to explain what it means for an element to be oxidized or reduced. You will also be able to state or solve for the oxidation number of a given element. You will be able to identify what an oxidizing agent is, what a reducing agent is, and also the spectator ions in an equation. So how do you know if reduction or oxidation is occurring? What you want to do is look for a change in oxidation state that appears after the reaction has occurred, and that will indicate to you that there has been a transfer of electrons from one species or one element to another. If there is a change in oxidation state, then you can classify that reaction as a redox reaction. Let's take a moment to review what the definitions of oxidation and reduction are and just go over some examples. So oxidation is a loss of electrons resulting in a more positive oxidation number. Let's take group 1 metals or alkali metals such as sodium. So when sodium is involved in an ionic bond, it will lose one electron, as is typical of group 1 metals, and upon writing the oxidation half reaction, you will see that when that loss of electron, that single electron has occurred, that electron will appear on the product side. Now, if we look at reduction and observe its definition to gain electrons, the result of that is a more negative charge or more reduced oxidation number. Let's take fluorine, for example. Fluorine, one of 7 diatomic molecules occurring in nature, will gain one electron when involved in an ionic bond. So upon writing its half reaction, you will see that fluorine, there are 2 atoms within the molecule of fluorine. Each of those atoms will gain 1 electron. So that's why there are 2 electrons written out here on the reactant side. The resulting product of that gain will be 2 fluoride ions. We can use this picture of a number line to help us gain a visual understanding of what is occurring with the oxidation numbers when oxidation or reduction occur. So notice when oxidation occurs and there's a loss of negative particles, the value of the oxidation number becomes increasingly positive. So you might remember from the previous slide, sodium in its neutral state, upon the loss of 1 electron, acquired a value of +1 for its oxidation number. It became more positive upon losing an electron. The same would be true for an ion. Say you had an ion with a +3 charged, and it continued to lose 2 more electrons. Upon the loss of 2 more electrons, it would then have an oxidation state of +5. Notice with reduction, upon gaining electrons, the value of the oxidation number becomes reduced or more negative. So for example, if you already had a negative ion with a charge of -1 or oxidation state of -1, and it went on to gain 3 more electrons, then you would have an oxidation state of -4. It's understandable that it can be difficult to keep these definitions for oxidation and reduction clear in your mind. So I want to offer you a memory trick that I found to be useful when I was learning about oxidation and reduction. So the first part of the phrase I want to teach you is oil. So oxidation is losing. What are we losing? We're losing electrons. The second part of the phrase is rig, so oil rig. Reduction is gaining electrons. This is what an oil rig actually looks like. Upon searching for images of oil rigs, I came across two more images that I found in an article. I thought it was interesting that I came across it during our period of distance learning because the creator of these images was envisioning what oil rigs that are non-functional could be used for in the future. The headline kind of says it all. So even though this has nothing to do with our lesson, if you're interested in looking the article up, it's by Michelle Lewis and was written or available online as of March 18th, 2020. So if oil rigs and social distancing due to COVID-19 don't do it for you, I have one more current event, or rather pop culture reference, linked to a phrase that I can share. So losing electrons is oxidation. The first half of the phrase is Leo, as in Leo the lion. Gaining electrons is reduction. So the second half is Gur. So like Leo says Gur. So with that, I give you the Tiger King. Feel free to use whichever phrase resonates more clearly with you. Now we're going to move on to review the guidelines surrounding how to assign oxidation numbers to elements. Remember, oxidation numbers are a simple way to keep track of electrons in a reaction. So the first guideline we're going to look at is that all elements in their free states have an oxidation number of 0. So the examples below show you silver, calcium, potassium, oxygen, and bromine, both of which, the last two, are both diatomic molecules, 2 of 7, that exist as double atoms in nature. Okay, so all of these examples, when they are present in a reaction, all have an oxidation state of 0. The second guideline we're going to examine is that monatomic ions equal the charge of the ion. So all of these compounds are ionic compounds. We have a cation and an anion present in all of them. So remember, magnesium is an alkaline earth metal or a group 2 metal, and those elements always have a positive 2 charge. Oxide, in this case, is going to be -2, and that is typical for oxygen, with a few exceptions that we're going to go over in an upcoming slide. In the next compound, aluminum chloride, aluminum, the metal, is the cation with an oxidation state of +3. Remember, it's in group 13. Chloride has a -1 charge. It's a halogen. And then lastly, looking at sodium oxide, sodium, an alkali metal, group 1, will have a +1 charge or oxidation state, and oxide will still be -2. The third guideline we're going to review focuses on hydrogen. So hydrogen is typically +1 in its oxidation state, except for when combined with metals, where it's -1. So in the first three examples, hydrochloric acid or hydrogen chloride, if it's a gas, nitric acid, or water, all three of these, hydrogen has a charge or an oxidation state of +1. Okay, now let's look at the exceptions. The metallic hydrides. So metallic hydrides means that there is a metal present. So this compound is known as sodium hydride. And because hydrogen is more electronegative than sodium, it's the non-metal, it gets to be the -1 ion, and sodium is still +1. Calcium hydride, same thing. Hydrogen has the -1 oxidation state, calcium gets to be the +2 ion, and then finally, hydrogen here, still -1, and aluminum is the +3, or the positive ion. The next guideline focuses on oxygen, which has an oxidation state of -2, except for in the instance that there's a peroxide present. Now, remember, peroxide is a polyatomic ion, and its oxidation state is -1. OF2 in this molecule, oxygen is going to be +2. All right, so let's take a look at these first two examples, carbon dioxide and water. In both instances, oxygen has an oxidation number of -2, and it's because it's more electronegative than the elements it's bonded to. And the exceptions here, we're going to examine the peroxides for now. In hydrogen peroxide and in sodium peroxide, oxygen has the oxidation state of -1. You can tell it's a peroxide because remember the formula for the peroxide ion is O2. And here, again, it's O2. Okay. Let's take a look at number 5. In molecular compounds, the more electronegative element is assigned the negative oxidation number. So here we have a binary compound, a binary molecular compound. I say binary because all of these have only 2 elements in them, and they're all molecular because they all are composed of nonmetals. So the first example, carbon monoxide, oxygen is the more electronegative element, so it's assigned a -2 oxidation state, and carbon is +2. So the algebraic sum, or the sum of the oxidation numbers of these ions, is equal to 0. This is the case with all compounds. All neutral compounds will have the sum of their oxidation numbers equaling 0. Let's look at ammonia next. Nitrogen here is the more electronegative substance, so it's assigned the negative oxidation value, and it is the -3 ion. Hydrogen here is +1. Silicon carbide, carbon is the more electronegative substance, so it has a charge of -4. Silicon is +4. And then finally, we saw this example in the previous slide as an exception for hydrogen, so we'll go over it here. In this molecule, oxygen is less electronegative than fluorine. Fluorine, if you recall, is the most electronegative element on the periodic table, so it will always have an oxidation state of -1. And in this case, oxygen gets to be +2. The next guideline focuses on solving algebraically for the oxidation number of a specific element. So in this example, we have sulfuric acid and sulfurous acid. Both of these molecules have polyatomic ions present. All right, let's take a look at sulfuric acid and assign the oxidation numbers to the elements that we already know, because we've already gone over the rules. So oxygen, based on the information on the previous slide, you should know has an oxidation state of -2 in this compound. And because of that, hydrogen gets to be +1. So hopefully you were able to figure out that sulfur is the element that we are going to be solving for algebraically. So when we do that, when we solve algebraically, we're going to be using this expression. Notice how the entire equation is set to equal 0, because all compounds that are neutral, all compounds, will have the sum of their oxidation numbers equaling 0. So let's take a look at each of these numbers. The 2 here, multiplied with the +1, that comes from the subscript on the hydrogen. The sulfur has no subscript, so we're just going to add in sulfur as +s without a coefficient, without anything to multiply it by. And then oxygen, notice, has a subscript of 4, so that means we have 4 oxide ions, so we're going to multiply 4 times -2 here. So the first thing we'll do is multiply, and now that we've done that, we're going to combine like terms, so 2 minus 8, that gives you -6. So now you're just going to add 6 to both sides to solve for S, and you should get +6 as your oxidation number for sulfur in this case. Now let's take a look at our next example. Here, again, we have sulfur, hydrogen, and oxygen, 3 of the same elements. And hopefully you guessed that we're going to be solving for sulfur again. But you can see that we will not be getting the same answer as in the previous example because we have different values for subscripts. So we're going to start with oxygen. Oxygen's a -2 here again. Hydrogen gets to be +1, and sulfurs are unknown. So here's our algebraic expression. We have 2 hydrogens again, so we're going to multiply +1 by 2. No subscript on the sulfur, so that remains unchanged. And oxygen, we're going to multiply the -2 oxidation state by 3 this time because that is a subscript on the O. Set the whole thing equal to 0 and solve. We're going to multiply first. Okay, and now combine like terms, 2 minus 6. That's going to give you -4. Add 4 to both sides to solve for S, and you get +4 for your oxidation state of sulfur. We're going to move on now to our final guideline up for review. And that guideline focuses on polyatomic ions. So this rule is similar to the rule we just went over, where the algebraic sum of the oxidation numbers in the ion is equal, not to 0 though, to the charge of the ion. So here we have the nitrate ion. We're going to set up the algebraic expression to solve for the element's oxidation number that is unknown. Hopefully you know that we're going to be solving for N because we know that O, being more electronegative, gets to have the oxidation state of -2. This is what the expression will look like. N has no subscript on it, so we're not going to multiply it by anything. O, or oxygen, has a subscript of 3, so you will multiply the oxidation state by 3 and set the whole thing equal to -1 because that is the oxidation state of the polyatomic ion. So first step is to multiply, and now we're going to add 6 to both sides to solve for N. Okay, hopefully you were able to determine that the oxidation number for nitrogen in this case is -5. Now we're going to take a look at some oxidation-reduction reaction examples. We're going to start with this synthesis reaction of magnesium plus sulfur producing magnesium sulfide. So the first element we're going to look at is magnesium. Notice that magnesium on the reactant side stands alone. We're going to start by assigning oxidation numbers to magnesium. So on the reactant side, because it stands alone, magnesium is 0. On the product side, where magnesium is in a compound, you may recognize that magnesium is a group 2 metal, so its oxidation state in this compound will be +2. Notice that magnesium is becoming more positive. Let's look at sulfur. Sulfur in its elemental state has an oxidation number of 0, just like magnesium. On the product side, when it's in a compound, it's going to have the oxidation number of -2. Now we're going to take a moment to consider which element is being oxidized and which one is reduced. Here are some things to recognize about oxidation and reduction. So the oxidized element will lose electrons. The oxidation number will increase or become more positive. And also, this is new, we call the oxidized element the reducing agent. Now, it's assigned that name of reducing agent because as this element is losing electrons, it is helping the other element gain electrons or become reduced. So that's why it's given the label agent, reducing agent as well. Were you able to guess that the oxidized element was magnesium? Notice we're going from 0 to +2. The oxidation number is increasing or becoming more positive due to a loss of negative particles. Let's look at the reduced element. It's going to gain electrons or become reduced, more negative. And because it's gaining electrons and helping the other element lose them, it's known as the oxidizing agent. So sulfur would be our reduced element. Now we're going to take a look at what the half reactions or the individual oxidation and reduction reactions will look like. So for magnesium, we're shown that magnesium in its elemental state is alone on the reactant side. And since this atom is losing 2 electrons, on the product side, you'll see it as an ion with a +2 oxidation state. The electrons that it's losing are also going to show up on the product side. Now let's take a look at sulfur's reduction reaction. So sulfur is gaining 2 electrons, shown on the reactant side, to become sulfide ion with an oxidation state of -2. Remember that the oxidized element will show electrons on the product side because they're being released, they're being let go. And the reduced element will show electrons on the reactant side because they're being gained. Notice how the electrons lost equal the electrons gained. That is one necessary step in balancing redox reactions. Let's take a look at another example. Here we have barium chloride reacting with sodium sulfate to produce barium sulfate and sodium chloride. Hopefully you were able to recognize this as a double replacement reaction. So we're going to do the same thing on this slide as we did with the previous example, in that we will assign oxidation numbers to each of the elements. Let's start with barium. Barium is also a group 2 metal. We saw a group 2 metal on the previous example. So barium ends up with an oxidation state of +2 in a compound. On the product side, barium, still in a compound, is still +2. So no change in oxidation state there. Let's look at chloride. Chloride's a halogen. Its oxidation state is -1. On the product side, it still has an oxidation state of -1. Sodium, alkali metal, is +1 on the reactant side, and on the product side, still +1. Now let's look at our next element. Well, we know oxygen, based on the guidelines, is going to have a -2 oxidation state. And on the product side, it will still have a -2 oxidation state. Algebraically, if you solve for sulfur, you will get +6 for sulfur's oxidation state on the reactant side and also on the product side. Now, one thing I want you to note is that this is the sulfate ion, SO4 -2. When you see a polyatomic ion appear on both sides of the equation, you can treat it as a single unit. So hopefully you recalled that sulfate has an oxidation state of -2. So when you see that, you don't have to separate the individual elements making up that polyatomic ion. Notice when you look at all of the oxidation numbers across the entire reaction, there is no change. So when there's no change in oxidation number after the reaction has occurred, then you cannot classify this reaction as a redox reaction. So this would not be an example of an oxidation-reduction reaction. Let's take a look at another example. Here we have a single replacement reaction involving chlorine. Remember, chlorine is a diatomic molecule, plus sodium bromide, producing sodium chloride and bromine. Bromine also being a diatomic molecule. Let's examine each of the elements to see what happens with their oxidation state. Starting with chlorine. Chlorine, in its diatomic free state, has an oxidation number of 0, and on the product side, present in an ionic compound, it has an oxidation state of -1. Next, we'll look at sodium. Sodium on the reactant side, alkali metal, is +1, and on the product side, it's still +1. Sodium, notice, is in a compound in both cases. Now finally, bromine. Bromine has an oxidation state of -1. It's a halogen on the reactant side, and alone in its elemental state, it has an oxidation number of 0. Let's take a look at how we'll classify these elements. So hopefully you were able to identify bromine as the element being oxidized. Notice it becomes more positive. That indicates a loss of electrons. From -1 to 0 shows an increase in its oxidation number. Bromine can also be classified as the reducing agent because it's helping the other element gain its electrons. Chlorine goes from 0 to a -1 oxidation number. it can do that by gaining electrons. So you'll notice the oxidation number is reduced or more negative. Because it is the reduced element, it can also be categorized as the oxidizing agent. Now let's take a look at sodium. Sodium, you'll notice, doesn't change in its oxidation number. So we classify sodium as our spectator ion. Spectator ions show no change in electrons, and therefore there is no change in oxidation number. It starts out as being +1 in its oxidation state, and after the reaction it still has that +1 designation. So because there's no change in electrons, we say that spectator ions, or in this case sodium, is not a participant in the reaction. Now let's take a look at the half reactions. Notice the bromide ion, it's going to lose an electron, but there are 2 bromide ions in the balanced equation. That's why there's a coefficient of 2 in the half reaction. So 2 bromide ions, each losing 1 electron, means that 2 electrons are lost. And then we also end up with bromine as a diatomic molecule on the product side. Looking at the half reaction for chlorine, notice chlorine, the diatomic molecule, is going to gain 2 electrons. So each chlorine atom will gain 1 electron. As a result, the products will have 2 chloride ions in the end. Now, if you look at sodium, notice that since sodium does not participate, there is no half reaction written for sodium. In these 3 examples that are coming up, we're going to assign oxidation numbers to each of the elements and then identify the element that's oxidized, the element that's reduced, and also if there's a spectator ion present. Let's start with potassium in potassium bromide. Potassium here has an oxidation state of +1 because it is a group 1 metal. On the on the product side, because it is still present in an ionic compound, it retains that +1 oxidation state. Can you identify how to categorize this substance? Hopefully you guessed that it was a spectator ion because the oxidation number does not change, and therefore it will not participate in the reaction. Next, let's take a look at bromide. Bromide, being a halogen, has an oxidation state of -1. Here, in its free state on the product side, its oxidation state changes to 0. So the way that an oxidation number will increase is due to a loss of electrons. Where would you categorize bromine? Hopefully you guessed that it's the element being oxidized or the reducing agent. Finally, if we take a look at chlorine, you'll notice on the reactant side, its oxidation number is 0, and on the product side, it has a -1 value. So that is possible due to its gain of electrons. Okay? Let's take a look here at our second example. Here in this synthesis reaction, we have silver and sulfur reacting to produce silver sulfide. Let's start with looking at silver. Silver in its pure elemental state has an oxidation number of 0, and on the product side, in an ionic compound, its oxidation number is +1. So that is possible due to a loss of electrons. Notice the oxidation number value increasing. So hopefully you were able to identify silver as the element being oxidized, also known as the reducing agent. Next, we're going to look at sulfur. Sulfur in its pure elemental state has an oxidation number of 0. And on the product side, present in an ionic compound, it has the oxidation state of -2. Notice that is possible due to a gain of negatively charged particles called electrons. So because it's gaining electrons, it is assigned the label of being the reduced element or the oxidizing agent. In terms of the spectator ion, well, there are no other ions or no other elements present, so in this case, there is no spectator ion. Let's move on to look at our next example. Here we have potassium chlorate decomposing to produce potassium chloride and oxygen. We're going to start with potassium. Potassium in this ionic compound as an alkali metal has an oxidation state of +1. On the product side, it's still present in an ionic compound, so it retains that value of +1 for its oxidation number. Notice that potassium's value does not change, so it can be classified as the spectator ion. Next, we're going to look at chlorine. Chlorine, you can solve for chlorine algebraically. In this case, is +5. On the product side, chlorine or chloride ion has an oxidation state of -1. Notice that the value of the oxidation number becomes increasingly negative. It becomes more negative, and that is due to a gain of electrons. How would you classify the chloride ion? Hopefully you chose the reduced element for its label. Lastly, we're going to look at oxygen. Oxygen in this compound has a -2 value, and then on the product side, in its pure elemental state, it has an oxidation state of 0. So notice that there's an increase in its oxidation numbers due to a loss of electrons, so it can be classified as the oxidized element or the reducing agent. So this example concludes part 1 of our oxidation reduction or redox series. If you are interested in learning how to write balanced half reactions, move on to part 2.